We have reached the end of the Devonian period and the advent of the Devonian mass extinction. The Devonian mass extinction is the second of the 5 mass extinctions recorded in the Phanerozoic rock record. Using Sepkoski's compilation of all marine fossil families for the Phanerozoic, you can see the decrease in biodiversity at the Devonian Carboniferous boundary, marked by the red dashed line. This diagram highlights the late Devonian and early Carboniferous periods. The late Devonian is split into the Franian and Famennian stages. As you can see in this diagram, at the boundary between the Franian and Famennian, there is a decrease in biodiversity, and another decrease at the Devonian Carboniferous boundary. Since the Devonian mass extinction was a prolonged marine biotic crisis, we need to ask the question, was it several events or one event? There seems to be 2 distinct events, one at the Franian-Famennian boundary, which is called the Kellwasser crisis. This crisis was a marine event that is marked by a distinctive lithophases of dark limestones and shales that formed in anoxic waters with no evidence of benthic fauna present. This may have possibly occurred due to the vertical movement of oxygen-deficient water masses. The second event occurred at the Devonian Carboniferous boundary. It is called the Hangenberg event and is marked by the deposition of black shales capped by sandstones. This is usually an indicator of a rapid sea level fall. This event appears to have affected both marine and terrestrial habitats. As with any mass extinction event, we look at what the triggers of the event may have been. With the Devonian mass extinction, we have identified 3 possible triggers. First up is environmental change. There is evidence of widespread anoxia in oceanic bottom water during the Kellwasser crisis due to high-frequency sea level changes. The Hangenberg event has also been associated with sea level rise, followed by a swift regression as evidenced by dark shales capped by sandstones. A second possible trigger is the evolution of plants, specifically land plants. As plants evolved, their size increased to the size of trees. They evolved seeds and other new ways of dispersal to colonize inland and upland areas. Their roots would break down soils and rock, which increases nutrient runoff to the sea, allowing for more algal blooms in the oceans. Widespread algal blooms could lead to anoxia in the oceans as these algae die off, and the decomposition process uses up the deep water oxygen. In addition, the increase of plant habitats on land and the subsequent spread of plants could result in a decrease in carbon dioxide levels in the atmosphere, cooling things down and potentially leading to glaciation. The third possible trigger is volcanism. The Veluli traps erupted on the Siberian Craton. This was a large flood basalt eruption that agrees with the timing of the Kellwasser crisis at the Franian-Famennian boundary. It could have destabilized the atmospheric greenhouse and changed oceanic chemistry, causing anoxia. The eruption of the Veluli traps, though, does not line up with the timing of the Hangenberg event. So if they were a trigger, they were not prevalent across the entire timing of the extinction. Terrestrial life was not affected to a great degree because there was little to no faunal life on land, and plants on land would not have been affected by marine events. Marine organisms, especially shallow marine tropical organisms, were hit the hardest, and entire reef systems collapsed. Tabulate corals, such as this example on the top, and rugose corals, like the one on the bottom, were hit very hard during this extinction due to the rapid rise and fall of sea level. Only 10 of 157 coral families survived, and tabulate corals lost 80 to 92% of their genera. The ostracoderms, the plated fish, vanished completely. Ammonoids took a hit and lost 88% of their species, but ultimately survived. Brachiopods, the most dominant shellfish of the Devonians, suffered. 7 groups were lost completely. There was a 27% family-level extinction rate at cooler, higher latitudes, but a 91% family-level extinction rate in tropical regions. In the late Devonian, which is marked by the pink band in this diagram, you can see that we had multiple orders of trilobites, which were the most common fossil in the Ordovician period. After the end Devonian mass extinction, which you can see in yellow at the very top, there were only 4 families of one order that survived the event to radiate in the Carboniferous. Between the Ordovician and Devonian mass extinctions, trilobites lost 57 families. Many of the organisms that thrived during and after the extinction were typically deep water or high latitude relatives of those that went extinct. Extinction was most severe in shallow tropical seas. On land, terrestrial plants actually experienced expansion, and after the extinction, the ecological gap vacated by the early jawless fish was filled by sharks. Overall, marine invertebrates were hit the hardest, with an estimated loss of 22% of marine families, which includes the loss of 79 to 89% of all invertebrate species. The primary Devonian reef builders, the rugose corals, the tabulate corals, and the stromatoporoids, never truly recovered due to profound changes in their ecology. The extinction left the reef systems so devastated that major reef building did not fully recover until the end of the Mesozoic era. The reef builders that did survive eventually evolved into the modern scleractinian corals after approximately 150 million years. We have reached the end of Module 10 and the Middle Paleozoic. In Module 11, we will investigate geology and life in the Late Paleozoic through the Permian mass extinction.